So, the formula says F is equal to G M1 M2 over R squared. Bye. So, the force exerted is equal to the product of the two masses. It's directly proportional to the product of the two masses and inversely proportional to the square distance between them. Do you see that? Alright, so that's how we start with our definition for Newton's gravitational law. From there, our questions can start. One of the points about Newton's gravitational law is that it's the distance between the centers of the two bodies. Alright, so it's not, if I'm standing here, it's not the distance between us, it's the distance between the centers of us. Alright? Alright, so I need a textbook. Someone have a textbook? Alright, so now we get a question from Newton's gravitational law on page there we go. And the examples in this book are terrible. Alright, so let's first do the manipulating of equations. Do you guys know how to manipulate an equation? So if I have this equation here that I'm working off of, alright, and I say the mass is doubled. Alright, so I double the mass. If I'm doubling the mass, then so I say the mass of both planets is doubled. Alright, so then it'll be F is equal to G 2m1 2m2 over R squared. You guys see that?
Yes, sir.
So then F will be equal to G 4m1 m2 over R squared, which means it'll be 4F. It'll be 4 times as big. Do you guys see that?
Yes, sir.
Is this new to you guys?
No.
Alright. So now, this is double the mass. Alright, so if I halve the distance between them, now I'm going to use my same formula. F is equal to G M1 M2 over R squared. Right, so I'm going to halve the distance between them. So now I'm going to say G M1 M2 over half R squared. Alright, so that's half the distance between them. So if I square a half, it will give me G is equal to M1 M2 over 1/4 R squared. You guys happy with that? Do simple maths, which means, F is equal to, which gives me F is equal to 1/4 F. Right, which means it is 4 times smaller. Right, you guys understand this?
Yes, sir.
Right, so this is on page 146 of your textbook.
Ma'am, there was a note about that.
Hmm?
The note stated, please now hold the scissors as well.
Yeah. Alright, so here we go. Alright, so we can say your school organizes a holiday tour to the moon, especially for all the physical science learners. The aim of the tour is research. The first investigation is to determine the value of the gravitational acceleration gm on the moon. For those watching at home, this is exercise 8, page 146 on your textbook. Alright, the first investigation determined the value of the gravitational acceleration on the moon. Joe organizes a small explosion on the roof of the hotel for the first evening's entertainment. During the explosion, a test tube is projected vertically upwards with initial velocity of 3.4 meters per second, and the test tube falls back to the ground, back to the roof 4 seconds later. Calculate the value of gm on the moon.
Ma'am,
Yeah.
will this be uploaded?
Yes.
Because I
Okay. Yeah, it's going to be uploaded. So I've also recorded the whole of the Newton second law. Yeah. Yeah, that's fine. You need to speak, that's okay. Alright, so. Sorry?
Thank you for listening.
Oh, it's a pleasure. Alright. So the first thing I do is I'm going to use the equations of motion. Alright, to calculate the gravity. Because remember, gravity is essentially acceleration. So I know that when something moves up and then down again, so I'm going to throw my marker. Moves up and then down again. What is my total displacement?
0.
0. Because it's moved up to the top and back down again to the bottom. The same velocity. Okay, so I have my initial velocity of 3.4. I have my delta x of 0. Okay? So I have my, so now we're doing question 4.1, exercise 8. Fine. Alright. Calculate the value of GM on the moon. Right, so now I'm saying I have my delta t is equal to 4 seconds. I have my delta x is equal, delta y is equal to 0. I have my vi is equal to 3.4. And I don't have my VF, I don't have my acceleration, which is what I want to work out. So from these values, can I calculate my acceleration?
Yes.
Yes. Alright. Now I don't have the memo here with me, so you're just going to have to be patient while I find the correct formulas. So I say delta x is equal to vi delta t. Sorry. Delta y is equal to vi delta t plus half at squared.
So when you use equations of motion for Newton's gravitational law.
So you use equations of motion when you need them. Alright, so when you're required to use equations of motion, use equations of motion. This question I think just happened to use them. As you'll see, when we get on to 4.3, then you'll see we start using the other ones. We'll also do question 5, I think. Okay. So, so we use our equations of motion and we calculate, oh not that example guys, I don't want to do this. Vi is 3.4 times 4 plus half a 4 squared. Can someone calculate a for me please? Okay, can I borrow your calculator?
And this is going to be in the physics group, right? General, right? General.
So I'm actually going to upload it onto YouTube.
Onto YouTube?
Yeah, and I'm going to send the link.
Yes, I'll use it.
Okay, so it's 3.4 times 4.
Thank you.
Pleasure. Okay, you guys want to stay for use the gravitational law or you want to leave? Okay. Okay, so I take this over, it's minus 3.4 times 4 equal to half a 16. Alright, so from there I say that divided by 8. One from 7. 1.7 meters per second, -2, done. Alright, so now I have my acceleration. Alright, so now it says Mount Shuttleworth's mass on Earth is 75 kilograms. What is his mass on the moon? His mass on Earth is 75 kilograms. What is his mass on the moon? does mass stay the same or does it differ between different planets? Is mass a scalar or a vector? Scalar, which means it's not dependent on gravity. So its mass on the moon will also be 75 kilograms. His weight on the moon, however, would be different. Alright. So now I'm going to do question 5 because that's a little bit more appropriate for Newton's gravitational law. So nice revision of equations of motion, I guess. And then Newton's gravitational law: a satellite orbits the Earth 12 kilometers above its surface. Mass. This is question 5. The mass of the satellite is 8.2 times 10 to the 4, and the mass of the Earth is 6 times 10 to the 26. The radius of the Earth is 6.4 times 10 to the 6. Calculate the force of the Earth on the satellite. So now, the first thing we do is we write down our equation. F is equal to G m1 m2 over r squared. So, what is my G? The universal gravitational constant, right? Which is (6.7 times 10 to the minus 11). So 6.7 times 10 to the minus 11. Alright, then mass 1 is 8.2 times 10 to the 4. My mass 2 is 6.4 times 10 to the 6. Alright, so that's divided by my r squared. So now it says, read the question again. It says, the satellite orbits the Earth 12 kilometers above its surface. It gives us the two masses. The radius of the Earth is 6.4 times 10 to the 6 meters. Calculate the force of the satellite on the Earth. So what's the distance between the center of the Earth and the satellite? Alright, so the values they give us. So basically what I'm saying is we have to add the 12 kilograms, okay, as the 12 kilometers to the distance, because it's 12 kilometers above, so that distance has to be included. So then we say 12,000 plus our 6.4 times 10 to the 6. I've done this wrong. 6 times 10 to the 24. Plus 6.4 times 10 to the 6 squared. Alright, so that's our equation here. And then we plug in our values. Alright, 801,775.68 newtons. Alright, so I just plug that into my calculator. Well, not my calculator, a calculator. Alright, any questions on how to use some gravitational law? It's actually pretty easy. Happy? Alright, thank you for letting me borrow your textbook.